In this video I want to talk about the polar form of a complex number and how it relates to multiplication. So recall that if you have a complex number z is a plus bi, non-zero, then the polar form for this complex number is given by an expression of this form. So if we can write z as r cos theta plus sine theta I, then this is called a polar form for the complex number. And in the case where we have theta between 0 and pi, that's illustrated in the sketch here. Right? So you can think of r as the length of that line segment, so in other words, the modulus of z, and theta is that the magnitude of that angle. Now, the great thing about the polar form of a complex number is that it works very nicely with multiplication. And in fact, we have the following. So if you have two complex numbers, z and w, both in polar form, so z r1 cos theta 1 plus I sine theta 1, and w r2 cos theta 2 plus I sine theta 2, then what does the product of z and w look like? Well, the modulus of z and w, of z times w, is just modulus z times modulus w. So we're going to have r1, r2 here. And now here's the nice thing. The argument for z times w is just the sum of the arguments for z and w. So if z is r1 cos theta 1 plus I sine theta 1 and w is r2 cos theta 2 plus I sine theta 2, then z times w is r1 times r2 cos theta 1 plus theta 2 plus I sine theta 1 plus theta 2. And this is just a consequence of the addition formulas for cosine and sine. So we have the following. Alright, so if you want to calculate ZW, so Z is R1 cos theta 1 plus sine theta 1 I, and W is R2 cos theta 2 plus sine theta 2I. And then we take out the R1, R2, and then we multiply out the two complex numbers here. Cos theta 1 plus sine theta 1I and cos theta 2 sine theta 2I. Right? Now that product, and we just apply the definition of multiplication of complex numbers, is going to be cos theta 1 cos theta 2 minus sine theta 1 sine theta 2. Right, that's the real part, and the imaginary part is sine theta 1 cos theta 2 plus cos theta 1 sine theta 2. Right, and now remember, what are the addition formulas for cosine and sine? Cos theta 1 plus theta 2 is cos theta 1 plus times cos theta 2 minus sine theta 1 sine theta 2. Right. And that's exactly what we have there in the real part of z times w. On the other hand, sine theta 1 plus theta 2 is cos theta 1 sine theta 2 plus sine theta 1 cos theta 2. And again, this is exactly what we've got here in the imaginary part. Right. So then we have ZW is R1 R2 cos theta 1 plus theta 2 plus sine theta 1 plus theta 2 I, as we wanted. So one should note that even when theta 1 and theta 2 are the principal arguments for Z and W. In other words, they both sit between minus pi and pi. It does not necessarily mean that theta 1 plus theta 2, right, not mean that theta 1 plus theta 2 is the principal argument of Z times W. And that's okay, right? Because remember, every complex number has many different polar forms. Now, what is really nice about this result is that it tells us how to interpret multiplication of complex numbers geometrically. Right, so let's look at two complex numbers, Z and W, with Z non-zero, and just for the sake of simplicity, we'll take W to have modulus 1. So let's write them in polar form. Let's say Z is R cos theta plus I sin theta, and W is going to be, say, cos alpha plus I sin alpha. Right? So we don't have an R here, right, because our R is 1, right, because the modulus of W is 1. So then if we apply our theorem, then what is ZW? ZW is R, right, note, the same as for Z, and the argument is theta plus alpha. So ZW is R cos theta plus alpha sin theta plus alpha I. Okay, so now let's see, if we draw a picture, what does this look like? Well, let's say here we've got Z, right? So its argument is theta, right? So that angle is theta. So if we look at Z times W, it has the same modulus as Z, which is R. So both points, Z and ZW, sit on the circle with radius R. But what is the argument of ZW? The argument is theta plus alpha. So what have we done to get from Z to Z times W? Right? We've rotated counterclockwise, this is for alpha positive, along the circle. Right? So what does this tell us? Multiplying Z by this complex number W rotates Z through an angle alpha, alpha being the argument of W. Right? So multiplying by a complex number with modulus 1 geometrically means we're rotating Z through an angle alpha. Right. So if alpha is positive, we're going counterclockwise. If alpha is negative, we'll go clockwise. Right. Now what happens if the modulus of Z is not 1? Well, if the modulus of, rather the modulus of W, if the modulus is bigger than 1, we're still going to rotate, and then we'll move outwards. If the modulus of W is less than 1, we're still going to rotate, and we're going to move inwards. Okay. So using the polar form for multiplication, we get some geometric insight into what's actually going on.